Hello everyone, thank you for coming to my presentation. Today I will talk to you about some new work called Orthogonality broadcasting and quantum position verification. This is joint work with René Ellistorfer, Ian George. Ian is also here at the conference, so if you want to talk to either one of us, please do. Myself and Eric Chitambar. So in my talk today, I will talk about a new tool that we introduced to primarily analyze the security of quantum position verification protocols, but it can be used a bit broader. So the outline for today will be as follows. I will talk about what is quantum position verification. I will define it for you. I will give a sort of short introduction, but if you want to learn more about it, please go to Florian's tutorial talk on Thursday on the subject. Then I will show you how some security proofs in setting works via mononymous entanglement games. And then I will introduce our new concept called orthogonality broadcasting. And I will tell you a little bit of from a foundational perspective and how you can use it to prove security for protocols. All right, so in position verification, you want to use a person's geographical location as a cryptographic credential. So what you want to do is you want to verify that some honest player is at his claimed location, and you can do this to then set up a key that can only be used at a certain position, for example, or send a message that can only be read at a certain place in space. So how it is often shown, it's like, let's say that we're on a one-dimensional line, and there's a prover placed in the middle, and around him is a coalition of verifiers, V0 and V1. And they want to verify that P is at this claimed location. And these two verifiers, they trust each other and they can have a joint strategy on how to verify this. So a well-known protocol is based on the BB84 QKD protocol, where you say, what if I input from one side a quantum state with the speed of light, I send it in, and it's one of the BB84 states, and from the other side I send the basis. Then I ask the prover to measure the qubit in the right basis and to answer the answer to both verifiers. And then you can sort of see that time is going up here. With the speed of light, these messages arrive at the same point. Then the prover has to act, and then he answers back. And then the verifiers can check whether the answer is correct, and they can check whether they received their answers on time. And then they want to convince themselves that P is at this claimed location. So when you consider attacks on these proofs, you should consider a setting where actually there is no P, and there is a coalition of attackers that want to spoof the verifiers by answering the challenge that they set correctly. So there's now going to be two attackers that by definition are not at this place in the middle, P0 and P1, that intercept the messages from both verifiers. And they're allowed to do some operations to it, and they can send some messages to each other. And then when they receive a message from each other, they have to answer correctly. But note that by the timing constraints, they only have enough time to send one message simultaneously to each other. So if they could talk back and forth, you can obviously break it, but there's not enough time to do that. That's sort of the trick here. And then there's two models you can consider. One is the model where these attackers pre-share entanglement, and one is where they don't. There's a very interesting background when they do pre-share entanglement, but here we're considering the setting where they don't, which is still practically relevant because it's orders of magnitude easier to send quantum information than it is to store entanglement for a long time. So in 2014, it was shown by TFKW that in this no-PE model, this BB84 protocol can only be attacked with success probability 85%, so it could be considered secure. And this was done via reduction to monogamy of entanglement games, and I'm going to show it to you. So the reduction goes as follows. So in this setting where you get from one side the basis information, this is classical information. So attacker P0 intercepts this information and she can keep it and send it on to the other attacker. And the other attacker intercepts the quantum information. And he's allowed to apply some sort of channel and keep something for himself and send something over to the other side. And then the first security proofs for this were limitations on the power of the channel that attacker P1 can apply. And it sort of went like this. So when we zoom in on the operations that attacker P1 applies, he gets some quantum input. He's allowed to apply some map to two registers, A and B. B is going to keep for himself, A is going to send over. And then later on, both of these registers learn about the value of theta, so computational basis or Hadamard basis. So we want to construct a map that attacks this protocol as well as possible. So we want XA and XB to be equal to the X of the input. And then via reduction to monogamy of entanglement games, you can actually use some nice operator inequalities on these entanglement games. And then you can show that any such map cannot perform very well. And actually, they cannot do better than 85%, this cosine squared pi over 8. So in this project, we are thinking a little bit, what if we want to extend security outside of this structure that works in the monogamy of entanglement setting? Or sometimes we have settings where the monogamy of entanglement bounds don't give us anything interesting. So in order to do so, we zoom in on this second part, on these operations that attacker P1 is allowed to apply. So we consider it as like a separate task, and we call it orthogonality broadcasting. So in this setting, your input is a state drawn from an ensemble, and that ensemble itself is drawn from multiple ensembles. So there's theta different ensembles, and within these ensembles, there are different states. So you can consider, again, computational basis 0, 1, Hadamard basis plus minus. Then you want to apply some broadcasting map. This could be somehow a restricted map with limited operations, or it could be any map. Then on the registers A and B, that are the outputs of this map, they both learn or they receive information about theta, and then they're allowed to apply some final operations. And then they win if XA is equal to XB is equal to the X of the input, right? So if it was computational basis, figure out it was the cat0 state. So what is the takeaway of the orthogonality broadcasting tool that we introduced? Well, in these QPV protocols that I introduced in the beginning, morally what attackers kind of want to do is they want to clone their inputs and send it to both sides, and then they can perfectly attack this protocol. But obviously you cannot do that because of no cloning theorem. So, but in fact you don't need to clone. You can do something slightly weaker. If you could do this orthogonality broadcasting perfectly, you could also attack these protocols. So understanding how well we can broadcast orthogonality on an input ensemble allows us to establish security of QPV protocols in this ensemble. And then you can also think of this from a foundational perspective. So what is possible with these types of broadcast maps? So you can, for example, consider the broadcasting map to classical registers or to quantum registers. And I'm going to give you an example that even classical orthogonality broadcasting is already interesting. So consider the following input ensemble. So in the theta is 0 case, you receive a trit that is either a 0 or 1. And in the theta is 1 case, you receive the superposition of plus plus 2 or plus minus 2. Note that if I would give you one of these 4 states, you wouldn't be able to clone it because the states are not mutually orthogonal to each other. However, you can show that there is a perfect classical orthogonality broadcasting strategy for this. So this is maybe surprising, but yeah, the notion of orthogonality broadcasting here, even with classical registers, tells you a little bit more. So if this would be a QPV protocol, you could actually break it with classical communication. And then how does this relate to quantum orthogonality broadcasting? So what we show is that if your amount of different ensembles that you pick from, so you have theta different ensembles, if it's equal to 2, then classical and quantum orthogonality broadcasting are equally powerful. So there's no advantage in using quantum orthogonality broadcasting. But we give a separating example when theta is bigger than 2. So we give a specific example. I'm not going to give it now. It's I mean, but you can look it up and or talk to us about it. You can separate these different classes by these examples. So we give an example that is provably does not have perfect classical orthogonality broadcasting protocol, but with quantum orthogonality broadcasting, you can do the task perfectly. And we can even go a little bit further with this. So we also construct a state ensemble where you can prove that there is a perfect quantum orthogonality broadcasting operation you can do, but this must send at least one input state to an entangled state, which is kind of interesting. So these 2 registers A and B are entangled for 1 input, and the protocol is still perfect. But you can show that there must be at least one state for this ensemble that gets mapped to an entangled state. So it actually shows that, for example, non-separable operations, orthogonality broadcasting, is separated from general quantum orthogonality broadcasting, and it's weaker. And now to think about security, so this is a foundational perspective, but now to think about how we can use this orthogonality broadcasting to prove security of QPV protocols, we are interested to prove that these QPV protocols cannot be attacked perfectly, and if we can give bounds on this orthogonality broadcasting step, we can prove that. So a natural extension is to think about not perfect orthogonality broadcasting, but to say, what if it's approximately correct, and what's the best we can do? So we actually prove a very general upper bound that you can apply to an input ensemble that is based on the fidelity and the trace distance between the states in the different ensembles. And we call it sort of a geometric uncertainty inequality. It uses the overlaps between the states within the Hilbert space of your input ensemble that undergo this broadcasting. And it's nice, so you're not relying on like that two states or two operators don't commute to measurements or whatever, but it's really about the states, and that makes it new. And when we apply our upper bound to the BB84 example that I was mentioning before, then we again retrieve the optimal approximate result, namely this cosine squared pi over 8. So our upper bound also gives this which is by the way tight also for the monogamy of entanglement games. Our upper bound also gives this result. But we can now use this upper bound to derive some new results that were not previously known. So we can actually show security for different QPV protocols for which we actually don't know how to prove security using the monogamy of entanglement games reduction. So, okay, this state ensemble might look a little bit that it comes falling out of the sky, and I guess in a way it does. But you can prove that if you apply the monogamy of entanglement reduction security proof to this state ensemble, that the operator inequalities that they use, they actually are trivial. They will not tell you anything interesting. They will just tell you a QPV protocol with these inputs, any attack will succeed with probability at most 1, which is like trivial, so it's not saying you anything. But what we can show with our new uncertainty inequality is that under a certain prior distribution, so not every state comes with equal probability, but that's fine. We can actually show that the probability to attack this QPV protocol, where these are the inputs, is upper bounded by 0.6035. So we can actually show security for this protocol. And this is not a QPV protocol that people previously considered, but it is nonetheless new, and we didn't have any tools to prove security for these protocols that seem very intuitively secure. And kind of interestingly, that this bound, so it's much lower, right, than the 85% bound of the QPV BB84 protocol. But you do have to pay a price, because you have to send qtrit input states instead of qubit input states, which is of course more difficult to do experimentally. But you get a higher rewards because your security parameter is much better. And if you would look at sort of a error per state that you can get, this is actually better than the BB84 protocol. So this brings up an interesting question, that if you get qdit inputs, can you like keep on getting better rates? So experimentally, this protocol might actually be more interesting than the BB84 protocol if you care about the experimental parameters that you need. And then secondly, we give a very similar state ensemble as given here. So here you can see that the first qubit is always this theta, right? So it's like 0, 0, or it's 1, or it's 2. But we give an example of a QPV input ensemble where sometimes we flip the two states around. So like let's say the second one will be 0, 2, you actually send to 0, or 1 and then the 1 minus 2, you would flip them around. And this is actually a setting that is completely out of the scope of the security reduction of the monogamy of entanglement games, but we can actually show security for this. So this is even, it's not that the monogamy of entanglement games don't give anything useful, they just don't say anything at all about such protocols, and our upper bound with orthogonality broadcasting does allow for this. So that seems to be very interesting, and maybe we can find out more about this. And with that, I want to thank you all for your attention. Thank you for listening.
Very nice talk. So it's time for question.
Thanks for your last talk. I wonder if your secret proof can be adaptive to when the two adversary shares entanglement.
Could you repeat the last part? Sorry.
So can the security proof be extended to the scenario where two adversary shares entanglement?
Not really. In this, it would be interesting if you could somehow get that to happen, but unfortunately not. No.
Thank you.
How about the other original attempt at quantum position verification, which was that Alice sent psi and Bob sends 0 or 1, and then the prover is to send psi either to V1 or to V2.
So you're talking about the routing protocol. Yeah, okay. It's funny that you asked that. There's actually some recent work that relates attacking the BB84 protocol to the routing protocol. So if you can do BB84, you can do routing. I can tell you about it. It's actually a couple months old from me. So in fact, yeah, this proof would also prove security for routing, but it's sort of via a separate reduction.
So let's thank the speaker again.